Okay, so good morning, ladies and gentlemen. We proceed to the defense of the doctoral thesis presented by Mr. Mohammed Mashayekni, entitled Inkjet Configurable Gate Array Towards Application-Specific Printed Electronic Circuits. The jury has been already considered. It is composed by Dr. Anthony So as vocal, by Professor David Castells as secretary, and by myself, Benjamin Nagel, as president of the jury. So, Mr. Mashayekni, you can start.
Okay, thank you for the introduction. Good morning, everyone. Thanks for coming. Today I'm going to present my PhD thesis named Inkjet Configurable Gate Array Toward Application-Specific Printed Electronic Circuits. I did my thesis at Universitat Autònoma de Barcelona, and my directors were Dr. Jordi Carabina and Dr. Luis Teres. So this is the outline of my presentation. First, I will give a brief introduction about printed electronics and the scope of my thesis. Then I will go through the objective of my thesis. Then I propose the basic idea of the thesis, which is the inkjet configurable gate array, and then the wiring methodologies and the techniques. And then the two main applications of the inkjet gate array for yield improvement and functionality personalization. And then I will show you some circuit implementations and improvement in the IGA and some conclusions. So basically, printed electronics is a new concept in electronic technology based on combination of new class of materials, printing technologies, and substrates. Well, if we want to categorize the printing technologies into some main categories, we would come up with some clean room high-performance processes, conventional analog printing, and digital printing. That I'm going to give a short introduction for each of them. Well, clean room processes, the most important ones are photolithography or nano-imprint lithography, are the high-performance, the technologies which provide the high-performance devices and circuits, and they are providing high resolution. But the question is that since they are mask-based and subtractive processes, so first of all, they're expensive, and they would cause some problems for organic materials, and some organic materials are intolerant to these technologies, and as they are very complex, consisting of mass preparation, light explosion, etc., it is expensive and complex. So basically, they are used for high-end applications where performance and miniaturization are playing important roles. On the other hand, we have analog printing technologies, where they are taking its heritage from newspaper industry, art industry. They're mass printing, roll-to-roll printing. They're having high throughputs. Some examples are flexography, gravure, offset, screen. And basically, they are still using mass, but in other forms, like screens, plates, cylinders, and stuff. So, and usually they are used for low-end applications where large area and flexibility are important here. The third category, which is the main scope of my thesis, is digital printing techniques. They are made of ink. They are basically inkjet, aerosol jet, electrohydrodynamic jet, superfine jet, and etc. In this printing technology, the patterns are defined and applied through computer-based EDA tools. So they are mask-based. There is no need to prepare any mask. So they're low cost. It allows the rapid prototyping of several geometries. Due to its concept of direct write and non-contact, the organic materials are more tolerant because there is no substrate, there is no pressure to the substrate. And due to its additive manufacturing concept, they are the layers are deposited, the materials are deposited layer to layer, so there is low material loss. But the challenge is still there is a very low resolution comparing with photolithography or some analog printing techniques. So we are proposing these technologies for individual personalization of organic electronic circuits. Okay, organic electronic association categorized the printer electronics applications into 5 main categories: lighting and photovoltaic, and 3 other categories which are basically the scope of my thesis, which are electronic and components, displays, and integrated smart systems, where electronics could go from the very low level of organic active devices like OTFDs and diodes to digital and analog circuits like RFID tags, display drivers, and in terms of analog, like conditioning, filtering, amplifying the signals. Having a flashback to silicon electronic technology and its design evolution, we see that from early 80s and 70s, circuit designers were used to draw polygons, rectangles, and transistors, and later gates to design the circuits. And then by improving the design methodologies, they had RTL, system on chip, network on chip, and multiprocessors. The key point here is that in 80s, everything was technology dependent, where the circuit designers needed to have a detailed information about the technology, the layers, and etc. So here we are in printer electronics. We are still in polygon, transistor, and gate level, and we need a detailed information about the technology. So comparing microelectronics with printer electronics, we see that microelectronics is a kind of fabless trend where almost 80% of the semiconductor cells are provided by 3 main foundries. There is a very widespread application domain, and at the middle of the way, there are several commercial design tools and process design kits that make it cause independency between the circuit designer and technology enablers. On the other hand, printer electronics is following a fab-based trend. It's a vertical business model, where there are several technologies, printers, inks, and etc. The application domain is still limited, and there is a high dependency between the circuit designers and technology. So what is the expected scenario for printer electronics? The expected scenario is that circuit and system designers can meet at the middle of the way with technology enablers in order to break the technology dependency by providing the process design kits, device modeling, DRCs, so that we can go from low level of rectangles and polygons to cells and libraries and circuit design methodologies. Talking about circuit design methodologies, I'm bringing the concept of ASIC here, which is application-specific integrated circuit design, which is a design methodology that is optimized for reuse by different applications. It's a successful business model, and it allows sign-off between technology and foundries, designer and foundries. Basically, ASICs could be divided into 2 categories of full custom and semi-custom. And what is the difference? In full custom, the circuit designers are dealing with low-level polygons and rectangles, and this is the lowest abstraction level in the technology, where the designers need to know detailed information about the layers, design rules, electrical parameter, and etc. On the other hand, semi-custom design technology, which also they call it cell-based or array-based, in which the gates are encapsulated into an abstract logic representation. The designers don't need to have detailed information about the technology, and they are mostly dealing with cells, component libraries, interconnects, and place and route algorithms. So we are proposing some aspect design methodologies, which is application-specific printer electronic circuits, equivalent term to ASIC, but for printer electronics. So what is the objective of my thesis? The objective of my thesis is to provide a new design manufacturing methodology being called INKJET-CONFIGURABLE gate array for personalization of electronic circuits, in which, first of all, complex processes like photolithography is used to fabricate transistor arrays, and low complex processes and technologies is used for individual personalization of circuits. For that, we are bringing two main concepts from ASIC and map it to ASPIC. And what are those concepts? Gate array and field configurability. And now I'm going to give detailed information about those two concepts. What is gate array concept? It is a semi-custom ASIC design methodology in which the manufacturing process is separated into two steps and separated in time. In the first step, we have the fabrication of array of unconnected transistors and wiring cells. They are located in regular positions, and large number of fabricated chips are stockpiled regardless of the customer order. In the second step, we just need to alter the metallization layer for creation of any individual circuit functionality. Basically, gate arrays are divided into two main categories of channel-based, in which transistors and wire channels are separated into the chip. Basically, they're placed in parallel or vertical or perpendicular way. On the other hand, we have channel-less, or being called sea of gate approach, in which all the chip is occupied by an array of transistors, and the metallization layer is realized on top of them. So what are the advantages of gate array concept? First of all, the cost of the shared mask are spread all over the applications, so that for the end user, only the final metallization layer is additional cost. And also, the metallization step is reduced. So it elevates the time and expense of multiple mask design and generation for custom design. What are its limitations? First of all, it's one-time programmable. As soon as you metallize, you customize the gate array, you cannot use it for other functionalities, and you cannot reconfigure it to other functionalities. The other limitation is that customization cannot be realized in the field, cannot be realized at home. It should be turned back to the manufacturer to provide the new mask and realizing the final interconnects. The second concept is the concept of field configurability. The concept of field configurability means that the chip can be configured in the field, at home, outside the factory. So there is no need to deassembling or returning it to manufacturer for individual personalization of the circuit. The most common one is the FPGAs, but the difference to gate array is that the chip is configured by using HDL or SDL languages, and those configurations could be permanent, like OTPs, like fuse or anti-fuse, or erasable, such as SRAM or flash memories. So the concept of inkjet configurable gate array. Inkjet configurable gate array, talking about those gate array concept and field configurability concept. Inkjet gate array, or IGA, is a design manufacturing methodology for individual personalization of electronic circuits, which is a hybrid approach to merge the benefits of clean room processes and digital printing processes. If we take those two steps of gate array into account, in the first manufacturing step, which is the fabrication of IGA bulk, we can take the advantages of clean room processes, where the master chip can take the advantages of high-yield clean room processes like photolithography to enable prefabrication of high performance and high resolution transistors in large volume. Obviously, it requires a complex process, because for transistors, you need a stack of layers. And in the second manufacturing step, which is the metallization of the gate array, we can use lower complex processes like digital printing to bringing the field configurability into the gate array concept, so that we can use maskless digital printing techniques such as inkjet, superfine inkjet, aerosol jet, or whatever. And printing can be employed in these printing methodologies can be employed in metallization step, which are having lower complex processes. What are the advantages of inkjet configurable gate array? First of all, it increases the functionality capabilities by using drop-on-demand printing. You can customize every individual fabricated master foil to its unique functionality, and also it allows the quick and accurate placement of wires, metallizations, at lower cost comparing to photolithography mask or EPRAM or SRAM fuse flash and whatever. The second advantage is that we can obtain high yield at system level out of mid yield or low yield at device level, at transistor level. And we are proposing the concept of fault tolerance for this second approach, in which we are adding an extra step to gate array methodology, which is basically used for the technologies where the yield is lower, the performance and yield is lower comparing to photolithography or clean room processes. And the IGA basic cell, IGA basic bulk is generated in those technologies where yield is important, an issue of concern. So we don't know if all the transistors are working or not, which of them are working or not. So we are adding the fault tolerance technique and adding an extra step to characterize the transistors, transistor arrays, and we can obtain the fault distribution of transistors. And then by adopting the failure map and knowing that which are the known good transistors, being called as KGOs, we can only customize those KGOs for any functionality. So, as we said, inkjet gate array is having two steps, and I'm going to talk about two steps. The first step is the fabrication of IGA bulk. So we divided the IGA bulk into four main cells: basic bulk cell, wire cell, interchannel wire cell, and I/O pads and power rails. But before going into details of each of these cells, I'm going to say that all along the process of generating the IGA layout, we have been using P-cell approach, parameterizable cell approach. What is P-cell? P-cell is a piece of code that whose instantiation or execution by EDA software allows the customization of certain design parameters to address the generation of a physical representation as a function of such parameter value. What are the advantages? First of all, it allows the IGA to be scalable to any technology. You can just take the technology file, stack of layers, and the design rules into account and build your IGA according to that technology. It is scalable to the size of the IGA. You can have your IGA small, medium, or large, depending the client's order. And it is reducing the design time because you don't need to deal with the polygons and rectangles just by writing a piece of code and defining some design parameter. You can generate the IGA automatically. You are optimizing the IGA, the area, and also you will have the unique device identification in the gate array, which can be used later on for characterizing the transistors if it is required. So going back to the different cells of the IGA, I will start with the basic bulk cell. We call it BBC. Basic bulk cell is the most basic element and mandatory element of the IGA structure, which is a small array of unconnected transistors, and they are responsible for building basic gates, elementary gates like inverters, NANDs, NORs, and etc. And the transistor arrangement inside the basic bulk cell depends on the logic family, digital logic family, for circuit implementation. I'm going to give a very slight introduction about the digital logic families in order to make it clear what they mean. Digital logic families could basically be complementary or unipolar style. Complementary MOS, or being called as CMOS, could be static, dynamic, transition gate, and stuff. Static CMOS is the most common one, and it consists of both N-type transistors and P-type transistors. The number of transistors are 2N, where the N is the number of inputs for the logic gate. Obviously, this style is the most robust one, and it is used for microelectronics, and it has high noise margin, high speed, and low power consumption because there is never a path between the VDD and GND, so the static power is zero, and it's reduced, the power consumption is reduced. However, there are some limitations for these styles for circuit implementation in organic electronics. And what are they? First of all, N-type semiconductor are still not as mature as P-type for printer electronics because of the slower carrier mobility. On the other hand, CMOS style requires complex technological processes to integrate and bring together both types of organic materials onto the same substrate, and it means that it is a high-cost technological process. Furthermore, there are many transistors for realizing any gate. It means that you need to have both the drive and load channels, both the drive and load networks, realizing the gates in parallel. So there are two n number of transistors, where the n is number of inputs, so it occupies large area on chip, and it is prone to be sensitive to hard faults. The other style is unipolar style. Unipolar or ratioed style is only made of N-type or P-type transistors. Due to organic materials limitations, we are only having P-type transistor, in which the load transistor is a fixed one. No matter what the logic is, the load is always one, and it is responsible for connecting the output to ground. And the drive transistors are realizing the logic function. So the number of transistors are reduced to n plus 1, n number of input, and 1 is the load transistor. So the area is reduced. And patterning and stability issues are minimized due to using only one organic material. However, comparing to CMOS, there are some limitations into this style. It has higher static power because there is a path between VDD and ground, and also because of different sizing of transistors in drive and load networks, there is an asymmetrical output rise and fall. Basically, there are two types of ratioed style. The first one is load-connected diode, in which the load transistor, as you see, the gate is connected to drain, and it is working like a diode. It's basically used for enhancement mode transistors, where the threshold voltage is negative. The load transistor is always on. It provides higher switching speed, and in this style, in order to have a proper output logic, the drive transistors needs to be sized much wider than the load. And depending on technology, this value could change. The other type is zero VGS load, where the gate and source of the loads are connected together, and it is used for depletion mode transistors, where the threshold voltage is positive. The load transistor is still always on, and in this style, the load should be sized wider than the drive. So by proper sizing of the drive transistor comparing to the load, we can implement inverter, NAND, and different logics. This style has been used in our target technology, and I will explain that later. So coming back to the basic bulk cell, we have used two types of drive transistors. As we said, we need to size them properly. So we have used two types of drive transistors, one for inverter and one for NAND gate. So as you see, we have 4 drive 1, 4 load, and 4 drive 2. The combination of 4, 4, 4 is scalable, and it depends on the ego size and the yield of the technology that we are building the ego with. And these small pads are there if the technology is suffering from yield issues and we need to have testing. If not, we don't need to provide any pads for the transistor. The second cell inside the IGA is the wire cell. The wire cell is a grid of unconnected interconnections and vias. The horizontal first metal and vertical second metal layers, which are isolated by dielectric, by passivation layer. The vertical ones are connected to transistors, and the horizontal ones are aimed to connect those transistor paths together in order to build any cell out of that. Wire cell is made of two types of wires, local wires and global wires. Local wires are inside the BBC, the basic bulk cell, and they are aimed to build the elementary gates inside BBC, like inverter NANDs and stuff. And global wires are used for connecting the elementary gates together and connecting those BBC together, or connecting the BBCs and already built logics to I/O paths. And the third and fourth cells are interchannel wire cells and I/O paths. Interchannel wire cells are very similar to wire cells, but they are surrounding the core of the IGA, and the aim is to connect the build logics, rows of BBCs together, or connect them to input-output paths. And the power rail and the I/O paths and power rails are the uniform array of paths and power rails, that supply rails that are distributed inside the gate array. So as a summary to the gate array architecture, it is composed of 4 basic cells. All along the design process, we use parameterizable cells. Basic bulk cell, as the most elementary cell inside the IGA, is composed of an array of drive and load transistors, and it is aimed for building elementary logics. The combination and arrangement of load and drive transistor depends on the scalability of the IGA and according to the size and yield, technology yield. Inside the BBC, we can use CMOS or unipolar logic families, and it depends on the technology and the available transistors that we have. In this term, we have used unipolar as the best candidate for organic electronics due to its lower transistor count and requiring less complex technological processes comparing to CMOS style. And wire cells and inter-wire cells are designed for connecting the built cells and circuits to I/O paths. So what is the second step in the gate array, in the INKJET-configurable gate array? The second step is the metallization of the IGA. What is the main difference between metallization of the gate array, silicon gate array, and metallization of inkjet configurable gate array? The main difference is use of digital printing. By using digital printing techniques, we can use EDA tools to define and apply the pattern, the metallization pattern. So we don't need to design and prepare a new mask, which is kind of the most expensive part in complex technological processes. So it is cost effective and it is rapid prototyping. The material loss is minimal due to additive manufacturing nature, and there is no removing material. So there is no need to using subtractive processes. And it enables the individual chip-by-chip personalization in the field. This is important, bringing the field configurability. And as the design is not mapped by mask, but just by bitmap or GDS file, you can change the design at even the very last stage of the production chain. However, in order to have this wire cell optimized, we have taken some optimization parameters, cost functions, into account. First of all, we have the cost. The wire cell inside the IGA needs to be sufficient to have sufficiently high integration density, because actually the density of the gate array is taken into account by number of transistors per area. So we are going to decrease the area that the wire cell is occupying. And also, it is optimum to have lower material waste in metallization step. And talking about performance, we need to have reliable wiring so that we don't find any failures during the wiring, so we increase the yield of wiring, metallization. And also, we need to have as much conductive wiring as possible. So what are the limitations for that? Because we are talking about complex processes like photolithography for eager bulk and lower complex processes like digital printing, like inkjet for metallization step, there is a huge gap between the resolution of these two techniques. Photolithography processes can provide in like less than 5 micron or even nanometer feature sizes. However, digital printing in the best alignment condition and the best conditions can provide around 20, 30 or even more feature sizes. And the other limitation is that digital printing produces different results on different stack of layers, different substrate, different conditions and materials. And this is undesired for a robust and promising metallization. So what we are proposing? We are designing a wire cell structure that is first make the most efficient use of real estate used for wiring in order to increase the density. A wire cell that obtains the highest metallization yield and conductivity to improve the performance. It should be compatible with digital printing techniques, with lower resolution techniques. And also, it reduces the effect of digital printing techniques during the metallization process. For that, we are proposing some drop-on-demand wiring methodologies. We are proposing 2 wiring methodologies to be used inside the wire cell of the gate array. One is line configurable methodology, which is based on printing fine lines, narrow lines, onto selective uncommitted wire cells to realize any electrical interconnection, and drop configurable structures, which is based on printing drops rather than fine lines. I will talk about them in detail. The first proposed approach is line configurable. The connection structure is composed of 2 key elements: predefined high-resolution cross of metallic tracks with via, and the final customization short track. So the idea is to connect those horizontal and vertical isolated metal layers together. So we are having a dielectric at the middle with a via opening and a square of metal 2 layer which is connected to metal 1, but it is not connected to the vertical metal 2. Just by printing a very fine line, connecting these vertical line to its similar layer square, we are actually connecting this one to metal 1. It means that we are connecting this layer to this layer. For failure analysis, like short circuit, open circuit, enough conductivity of this method, we propose some wire test vehicles similar to the ones inside the wire cell of the gate array. So the idea is to, by printing the yellow lines, we are aiming to connect TI to BI. And this is the equivalent connection. There is a very important drawback in this technique, in this methodology. Printing long, fine wires, which are sometimes in 80 or 100 micrometers in length and 10 or 20 in width, is not very easy by using some low-resolution digital printing. For example, taking inkjet printing into account, which it is not suitable for printing very fine lines onto these structures. So for that, we are proposing drop configurable structure. This structure is composed of 2 key elements, via banks and drops. So the algorithm is similar. We have two metallic layers isolated, and the idea is just by leaving drops here rather than fine lines, fine long lines, the idea is to connect the exterior metal 2 layer to metal 1 layer. So for that, those layers are isolated by passivation, there is a via opening, the interior square is connected to metal 1, but it is isolated from its own layer, but exterior square. So just by leaving a drop on top of the via bank, we call this via bank. On top of that, we are connecting the exterior side to the interior square, which means that we are connecting the exterior side to the first metallic layer, which means that we are connecting this line to this line, if it is needed. We also designed some wire test vehicles similar to the wire cells inside the gate array, and you see the unconnected, connected, and equivalent connection. What are the advantages of this method? It eliminates the limitation of previous implementation, so because there is no need for very fine and long lines, it is just by leaving a drop. And due to its zigzag nature, we can improve the circuit density in the wire cell. And also it enables the use of several printing technologies with lower resolution, like inkjet. Before, by inkjet, we were not able to print very fine lines, long fine lines. But now, because we only need to leave some drops, inkjet is also suitable for this. We also designed another test vehicles for checking the repeatability of the connection banks. We designed some series of these wire banks, 4, 2, 4, 8, 16, and 32. And the idea is to leave wires, leave drops on top of all of those banks and check the resistance between two paths. So which metallization techniques, which digital printing techniques did we use for metallizing those wire test vehicles? We used superfine inkjet, which is the very high resolution digital printing technique. In this work, we use 6, 12, and 20 micron lines for line configurable methodology. And in this technique, the printing pattern is a very simple text file. We also use aerosol jet, which uses the focused aerosol spray. It is mid or low resolution, and in this work, we use 15 micrometer lines. And the printing pattern is the GDS2 file. We also used inkjet printing, which is the mid or low yield resolution comparing to other digital printing techniques. And we only used this technique for drop configurable structures because of the challenges that I talked about before in line configurable structure. The printing pattern is a simple bitmap file, and we used the MIP 2831 equipment. We also use electrohydrodynamic jet. You cannot see that in my thesis because when I already have deposited the thesis, I did the stage in University of California, San Diego, using this technique. So they are still being developed and under investigation, so I couldn't have been able to provide some results. And finally, we used similar technique as the wire structures, photolithography, as a reference to check the conductivity and the compatibility of digital printing techniques. So this is a table of which techniques are used for line configurable and drop configurable test vehicles, and those are the unwired fabricated test vehicles. Drop configurable wire test vehicles, line configurable wire test vehicles, and wire chain. This one is consisting of 32 wires. So SIJ, superfine jet, the first one for line configurable wiring of wiring methodology, we used width of 6 micron, 12 micron, and 20 micron, and those are the results. We used SIJ also for drop configurable, and we see that for the bank width of 50, 70, we have very nice results, and also for the spacing between the bank width of 30 or 50, we have nice results. And also for 32 serial bank chain, we see that all the wires are placed, all the drops are placed accurately. We also used aerosol jet, which is not the best results because due to its continuous printing nature, so as you see there are some spreads all over the substrate which causes some failure. And we only use that for line configurable structures. And finally, we use the inkjet, which is showing a very nice results for drop configurable, for different width and spacing. And as you see, the drops are printed very accurately on top of the banks. And those are the nice photolithography results for both line and drop configurable wiring structures, which are taken into account as reference. So for the results of line configurable structure, we measured 32 samples for each technique. We see that there are many faults for 6 micrometer width SIJ, where for 20 micrometer width we have here number of failures. This failure for photolithography was, we cannot say that 1 out of 32 could lead to 97% yield, because if we increase the number of samples, I'm sure that this yield could be increased to 99 or almost 100%. And the sheet resistance of the wiring of the printed wire, as you see for SIJ, it is very similar to photolithography one, which shows the synergy between the digital printing and the photolithography pattern. And as you see, for the histogram of the measured resistance for photolithography, the resistance value and also for SIJ, the resistance value is concentrated for a very low value, while for AJ we see very high dispersion and variation in the results. For drop configurable structures, we see almost 100% yield under good alignment conditions. And we came up to the idea, to the resolution that the minimum width of 50 and minimum spacing of 50 would be ideal for the wire banks. And comparing inkjet printing, SIJ printing, and photolithography, we see that the average resistance per bank is very close, between 10 to 20, although the inkjet printed resistance is 2 times more than photolithography. But comparing to the on resistance of transistors inside the gate array, which are in order of kilo ohm or mega ohm, these values are negligible. So, as a conclusion, as a summary to this step, we propose line configurable and drop configurable structure wiring methodologies. Yield between 70 and 97 were observed for line configurable, but the issue with that was printing fine lines with low resolution printing technologies like inkjet. So we proposed drop configurable method, in which only by leaving drops we can have the electrical connection. Yield of almost 100% was observed for this methodology, and the resistance of in order of 10 to 20 ohm per bank was observed. And this resistance is negligible comparing to the on resistance of the transistors inside the gate array. So, as we said, EGA has 2 advantages, and one of them for yield improvement. And now I'm going to talk about EGA for yield improvement. Some of the printing technologies, like non-clean room technologies, like inkjets, are suffering from process variation and finally yield issues. Yield means the number of working devices out of total number of printed devices. So there is a problem. Mid-yield at device level would end up to very low yield at system or circuit level. Why is that? Because if we have 50% yield in device level, we don't know which of these transistors are working and which of them are not. And if we use even one of non-working transistors for wiring, it means that the whole circuit might fail. So one solution is we customize several number of EGA foils in order to have at least similar functionality, in order to have at least one of them working. But the question is that what if we don't have even one of them working? Because the yield and the failure map is variable from run to run and sample to sample. So the real solution is fault tolerant technique. And what is that? we say let's characterize transistor arrays in every foil to extract the fault distribution. So we are adding an intermediate level step to the inkjet configurable gate array steps. So the first and third steps are similar to gate array in silicon, but the second step is characterizing of OTFDs by means of an automatic characterization environment to report the distribution of KGOs, good known transistors, known good transistors. This is the implementation flow. So in the first step, we use the cell-based IGA architecture generator to generate the layouts of the IGA bulk. We also report an XML description file where it reports some information about the transistor, dimensions, location, and stuff. We fabricate that layout, and we have different foils. In the second step, we characterize each fabricated foil and report its own failure map. In the third step, we take the final circuit that we are going to implement on top of the IGA, the Verilog netlist. We take the layout and we take the failure map of that individual foil. And then we customize that individual foil taking its own failure map and functionality into account. And we will have several customized foil to a functionality with different failure maps. So we went ahead and we designed some gate arrays for all inkjet process. We used a diode-connected logic style in which the transistors were working in enhancement mode. The combination of BBC is 444, drive 1, load, drive 2. The ratio was 1:8 and 1:16 for inverters and NAND 2s. Large pads were designed for each transistor to be tested. And you see there are 210 number of transistors and the chip area. We characterized each fabricated foil by using automatic characterization environment developed by my colleagues at CNM. And we saw that there are different yield and failure map distribution inside each foil. As we see, for two different foils, the green ones are working, those are the transistors, and as we see, the failure map and the known good transistors are located differently inside each foil. So, as a proof of concept, we tried to customize each of the two gate array foils to one similar functionality of a multiplexer. And this is the layout for two different foils. As we see, there are different known good transistors or bad transistors, and according to its failure map, we are leaving drops or lines in order to realize the functionality. However, due to the fact that this process was used during the TDK project, TDK4P project, we couldn't follow up because in the last fabrication run that we fabricated these foils, there were some problems with the fabricated transistors, so we couldn't have some higher yield in respect to both wiring channels and transistors, and we didn't have further runs. So as a summary to IGA for yield improvement, we can say that many non-clean room processes are currently suffering from process variation and low yield. So this low yield at device level would cause very low yield, almost 0% in system level. And this yield is variable from run to run and sample to sample. So we propose the fault-tolerant technique to improve this yield at circuit level by just adding an intermediate step to manufacturing steps, and we are only customizing using the KGOs, known good transistors, for customization step. The other advantage of IGA is IGA for functionality personalization. This is the most feature to address about the IGA. which is hybrid approach to merge the benefits of clean room photolithography processes, where the master foil can take the advantage of high yield and high performance processes for basic devices, transistors, and it can take the advantages of digital printing for personalization of the IGA at home, which ends up to individual chip-by-chip personalization, which means that each fabricated foil can be customized to its unique functionality. Then we are increasing the functional capabilities of the IGA at lower cost comparing to OTP, RAM, or other techniques. And this is the implementation flow, which is very similar to silicon gate array. So in this one, the second step in previous one, which was the characterization of OTFDs, is withdrawn because we don't need to characterize the OTFDs as we are sure about the almost 100% yield in transistor level. So we went forward and we designed some IGA bulks for photolithography technology. They were fabricated at New Drive CPI. We used minimum channel width of 4 micron for interdigitated transistors, and those are the IV transfer curves and mobility of the transistors. As we see, the threshold voltage is very positive, so we are using we are in enhancement mode transistors, and we are using 0 VGS style. So the BBC is made of drive 1, drive 2, and load. Load is dimensioned wider than drive 1 and drive 2. The ratio is 7 and 14. This is the optimum ratio after some trials. This is P-cell based, so we can change the dimensions of the transistors if required. And this combination of, for example, here 333 is scalable according to IGA size. And this is the wire cell built of 4 local wires and 5 global wires, and it is scalable, obviously. And also we use drop configure method for interconnections in order to use inkjet for customization. So we did some, not we, they fabricated the IGAs at CPI, some small prototypes and large prototypes. This is the picture of the small prototypes, build of 54 number of OTFDs. And yeah, the total area of the chip is 1.4 centimeters square. And there are some testing pads. You might ask why they are here, as this is a photolithography, because we designed these IGAs also for process development. So we needed to test transistors not to see if they're working, but to know the behavior of them for other reasons. We also designed some large prototypes having 252 number of transistors without testable pads here, and the total area of the chip is 3.7 centimeters square. So comparing the circuit density with the state-of-the-art programmable logic arrays, we see that we are increasing, although the number of transistors in the gate array is lower than programmable array logic and C of transition gate. The thing is that the chip area is almost 1 order of magnitude smaller than those fabricated arrays. And finally, the transistor per centimeter square and centimeter square per minimum channel length is improved dramatically compared to the other ones. So as a summary to this step, we are saying that clean room processes like photolithography produce high performance and high resolution device with high yield at device level. So we don't need to test each individual transistor to extract the failure map, as we don't expect to have any. Digital printing can be used as metallization technique for individual personalization of the gate arrays. We designed small and large gate array prototypes with 54 and 252 number of transistors respectively by photolithography technology. And comparing to the state-of-the-art programmable logic arrays, we are improving the circuit density from 0.35 and 7 to 17 transistor per centimeter square per minimum channel length. So I'm going to show some circuit implementations of the gate array. In the gate array, I used the inverter and NAND 2 gates as the most elementary and basic logic circuits, gates. As we see, we are having the drop configurable structure for the wire cell. So just by leaving some drops, we can, and using only 2 transistors, 1 drive and load for inverter, and 2 drive and 1 load for NAND 2, we are implementing these 2 gates. It didn't used to be like that. Those are the inkjet printed devices, inkjet printed, inkjet wired inverters. As we see, there are the drops. I don't know what happened here. And these are the results of the inkjet printed, inkjet wired inverters. We wired 3 inverters on different corners of 1 IGA. And we see that there is a slight variation in the static characterization of static behavior of the inverters, and this is due to the fact that they are being wired on different corners of the IGA, and the parasitic effect of those wiring cells is affecting a bit the drive to load ratio of the transistors and the output curve. But more interestingly, we compare the inkjet wired inverters with photolithography wired inverters. And we see that there is a very good matching. If we design a mask for inkjet, for inverter printing, for inverter implementation, or we just use inkjet for implementing inverters. And we see that there is a very good match between those 2 techniques. We also did the dynamic characterization of the inverters, ending to the propagation delay of 1.1 microsecond, and this is later on being used for measuring the expected frequency of the ring oscillators. We went forward, we designed some 5-stage ring oscillators. Before implementing the same ring oscillators inside the gate array, we implemented them. We kind of designed them in full custom manner to see what is the maximum frequency of the 5-stage ring oscillators, then to take it as a reference and compare it to inkjet wire ring oscillators inside the IGA. We designed 30 number of circuits, and we came up to the maximum frequency of 617 kilohertz for ring oscillators, with the maximum output swing of 30 volts. Then, then we inkjet wired similar circuits inside the gate array. I couldn't fit all the inkjet wired ring oscillators in one image, so this is just a build of 3 drive transistors. It's part of the ring oscillators. And here is the results. The final frequency is 74 with almost 8 volts peak-to-peak voltage. Taking the propagation delay of the inverters, we expected to have the frequency of, for 5-stage ring oscillator, we expected to have frequency of 91 kilohertz, and we are having 74. It is not very accurate, and the reason is the parasitic effect of the wire cells inside the IGA. Okay, finally we came up to the idea of improving the density and some other criteria inside the IGA. So we designed cell-based IGAs. What is cell-based IGAs? Cell-based IGA is a new implementation of IGA where in BBC the transistor arrays are replaced by logic arrays, by inverters and NAND 2 in this case. What was the idea? We were planning to improve the density. Why? Because for just, as you saw, just for having one inverter, we needed to occupy 2 drive and load transistor and a wide and a big wire cell section of the IGA. But here, the inverter is encapsulated into one small logic cell, and we are using that with 3 ports, with 2 ports, input and output, And we are using that for building more complex circuits. So we are improving the density, we are improving the metallization yields. Why? Because imagine we are going to have multiplexer implemented inside the IGA. So we need to use almost 50 number of drops in cell-based IGA, where in transistor-based IGA, where for cell-based IGA, we just need to connect 3 NANDs and 1 inverter. So this value is reduced maybe to 5 or 7 number of drops. So when we are printing less number of drops, it means that we are increasing the metallization yield. We are reducing the risk of faults. And also the customization time is also improved because we are printing less number of drops. Comparing to our transistor-based IGAs, for the same area, 252 number of transistors for transistor IGA is now changed to 728 number of transistors for cell-based IGA, which finally almost have 3 times of density. And this is a small prototype of cell-based IGA, and we see that instead of having transistor arrays, we have inverter and NAND2 arrays. Conclusion. We proposed inkjet configurable gate array as a new design manufacturing methodology to map digital circuits on top of prefabricated transistors in 2 separated manufacturing steps. It brings the advantages of gate array and field configurability from ASIC design methodology and map it to ASPEC. Small and large IGA prototypes with 54 and 252 transistors with density of 68 per centimeter square were designed and fabricated. Line configurable and drop configurable wiring methodologies for customization of IGA was proposed. The yield of between 70 to almost 100% was observed for digital and photolithography technique for wiring of line configurable wire structures. And also the yield of almost 100% was observed for drop configurable structures. 20 number of ring oscillators were inkjet wired and photolithography wired inside the gate arrays, demonstrating the synergy between high resolution photolithography patterns and mid or low resolution digital printing. Maximum oscillation frequency of 74 kilohertz for IJ wired ring oscillators inside the IGA was observed. And we also proposed the idea of cell-based IGA as a new methodology to improve metallization yield, time, and the area. Number of transistors is increased from 252 to 728 for the same area, and moving from 17 to 49 transistor per centimeter square per minimum length, moving from transistor-based IGA to cell-based IGA. So what is the future work? Several combinational, like multiplexer, encoder, decoder, and etc., and sequential circuits like D flip-flop, shift register, counter, and etc., have been designed and fabricated in full custom manner to be taken into account as the reference. And they are opening the door to the real-world applications of printer electronics like display driver circuitry, RFID tag, and etc. And as a future work, the characterization, improvement of those circuits are being undertaken. It is planned to map the similar circuits inside the gate arrays. And these circuits are also going to be mapped into cell-based IGA to compare the results. And regarding the IGA structure, several improvements, especially in wire cell, are being undertaken in order to improve the parasitic, reduce the parasitic effect by kind of reducing the overlap of metallic layers for capacitance and having wider metal layers for decreasing the resistance. Parameter extraction and device modeling of the OTFDs is being investigated, which is opening the door for analog domain, analog circuit design opportunities. Finally, I managed to publish 5 journal papers as main author and co-authors, and some conference presentations. Thank you for your kind attention. So.
Thank you very much for your talk. So now it's time for questions from the members of the jury. So the first jury member to ask your question will be the vocal. So it's your turn.
Thank you. Thank you, Mohammed, for a very interesting presentation and a very interesting thesis. My first question is about your introduction and a general question, really, on how you see organic devices and organic transistors and organic systems on chips progressing, given that we have organic photovoltaic devices and organic LEDs and now organic TFTs. How do you see this going?
Well, obviously there has been a tremendous improvement in design of organic materials, organic printing technologies, and circuits being implemented. And well, obviously, as I see organic electronics, basically printed electronics, is not going to be a competitor with microelectronics, but it is opening some door to some real-world applications where miniaturization and high performance is not required, but more like flexibility and large area is being applied. So yeah.
Thank you. Your drop connectivity scheme shows a much higher reliability than the line configurability. How much of that do you think is due to the design of your bank? Because it kind of contains the drop quite nicely. How much do you think that is due to the design of the bank and not the intrinsic printing mechanism itself?
Well, I think there's a trade-off between both of them because yeah, the printing equipment is affecting a lot. But why is that? Because in line configurable structure, we need to print very fine and long lines. And this is happening, this is causing some problems, although these problems are coming from the digital printer, but the structure is the reason for them, because it requires printing fine lines. But when it comes to drop configurable structures, as the printer is going to do very simple job of just leaving some drops, very normal drops, not very tiny, in 40 or 50 micron in width, in diameter. So I think both the design and the printer equipment is collaborating to have kind of more promising results compared to the previous style.
And was it only ever one drop placed, or were there multiple drops placed in a single location?
Yeah, that's a very good question. It depends on the used ink, the conductivity. Actually, obviously there need to be multiple drops in order to achieve the conductivity. In the last stage that I have in University of California, we managed to print just one single drop. And when we checked the conductivity, it was not conductive. So we increased the number of drops to 5. There was conductivity, but still comparing to photolithography, not enough. But when we increased that to 10 or 15, we had nice conductivity. So I believe that there needs to be multiple drops accurate in the same location, same origin, in order to satisfy the desired conductivity.
Thank you. So if I may move on to the main part of your thesis, the fault tolerance and the mapping of the devices.
Yeah.
To test every device obviously takes some time. I wonder if the process of testing a device might actually damage the device, because mainly these devices may be sensitive to ESD
Yeah,
events and such like.
yeah. The thing is that, as we see here, there is a very nice automatic characterization environment developed by my colleagues at CNN, where it allows the characterization of each foil, which like having some 200 number of transistors, being tested for different bias stresses in maybe like 5 minutes. It is an automatic device characterization environment which is reporting very nice Excel files, micro Excel files, which are providing different bias stresses, taking photos and giving detailed information about the device behavior. And thanks to that, the characterization of the foils is not taking more than some few minutes.
Yeah, because there doesn't seem to be any kind of pattern that I could discern from your two maps there. So I just wondered if the testing procedure introduced some pattern or failures. But
You mean an expected pattern of, because this is the failure pattern, which is the green ones are the working transistors and the non-green ones are bad transistors.
yeah.
So I don't exactly get your question. If you mean the expected pattern, because this is variable.
Well, yeah. Well, I wondered if because the tester, I guess, does it in the same pattern every time.
Yeah.
So maybe the same, maybe the beginning of a row or something would experience, for example, an ESD event or something, as the substrate or the tester moves. So I just wondered if the actual process of testing would blow transistors instead of testing them.
I don't think so, because as we have designed very large paths for the transistors to be tested, which are almost 2 times bigger than the transistor itself, so these paths are, the transistors are being pinged by these paths, and the transistor, I mean the active part is not being touched or damaged at all.
Okay. I noticed on some of your schematics of the final circuits, you had a line for VSS, a horizontal line, and the line 65, I think it was.
65?
Yes. And a line for VSS and a line for ground. Now, are they different? Is there a reason for?
Yeah. The reason is that for this technology, we are having enhancement mode transistors with negative threshold voltage, which are ending to diode connected load topology. So for that, we are connecting the gate not to the drain, but we are connecting the gate to minus VSS.
Ah, I see.
Yeah.
Okay.
So this is why we are having 3 power rates.
So you have 3 rails
Yeah.
for this. I see. Okay. For the cell-based version of the IGA, it seems to me that the reliability of your printing, your drop printing, is quite high. But the reliability of the transistors is quite low, about 50%, according to the testing.
Yes.
So, would this really be an improvement in the overall yield?
You're right. Yeah, I think I didn't make it very clear, because we have 2 types of EGAs fabricated. One of them is the all inkjet EGAs, that we cannot go from transistor-based EGAs to cell-based EGAs. What is the reason? The reason is that we are not sure if an inverter would work. So we are still staying in transistor-based EGA, where we test each transistor. But the other type of EGA is the photolithography EGAs, where we are having 100% yield in transistor level, almost 100% yield in transistor level, so we can go from transistor level to cell-based level. So all the custom designed inverters are working perfectly. So we are moving to one higher hierarchical level.
I see. So you don't anticipate doing cell-based on the all inkjet then?
Photolithography.
I see.
Yeah.
Okay. And looking forward now, you mentioned spice modelling or analog modelling of some sort. Well, have you looked into any kind of which OTFT or silicon-based spice model you might be using? Have you had any ideas on that yet?
Well, recently the idea is still staying with the normal PMOS organic semiconductor that we are having in being provided by New Drive and fabricated at CPI.
Mm-hmm.
And we still don't have any planning to go for silicon-based devices, but the improvement that is being looked forward is just to designing a tool to double gate structure in order to kind of shift the threshold voltage in order to improve the behavior of the transistors. But adding some inorganic materials to the substrate is not still
right. That wasn't quite what I meant actually, but I meant which spice models have you looked at or
okay.
are anticipating to use?
Okay, yeah. Well, actually, I haven't been involved in modeling process at all, but as far as I know, because I haven't done anything yet, but as far as I know, they are doing a very low level, I think level 1 or level 2 spice model where just very elementary parameters of the device are being extracted.
Okay.
Yeah.
Well, I have no further questions actually. Thank you.
You're welcome.
Okay, thank you. So now it's the turn of questions of Professor David.
Okay, thanks for your presentation. It was a pleasure to read the thesis. I have some comments about the presentation and maybe about the manuscript also.
Sure.
First, in slide number 10, so I come from more software perspective,
Yeah.
and I don't agree with this slide here.
Yeah.
You say open, so this is about the description of circuits at the hardware level.
Yeah.
So I guess that once you get to the system on chip, you have OCIP, but above that, you probably describe things with UML or CSML or something like that, but not with software applications like OpenMP and MPI. This is software thing. But this I know that this is not your topic. One question about so the first one is important one, I think, is about this thing about characterization. So you with inkjet printing, you say you characterize, but then you go to silicon, well, to clean room facilities, and you say that you have a 100% yield. That's what you said.
Yeah.
Is this realistic?
Well, actually, the results showing that. Yeah, the thing is that when we are fabricating the stack of layers for OTFTs, like it requires 5 stack of layers in OTFTs. When it comes to inkjet, we have some issues with inkjet printing, like short source drain, short between the gate and source or drain, and other issues. But when it comes to photolithography and etching process and photoresist, well, the things are more reliable, and the results show that unless there are some very minor errors, faults, we can expect something like 100% yield.
So this means that we don't need any fault tolerance at all.
No,
when
for
using
photolithography, we don't need fault tolerance technique.
So then the conclusion would be that we don't need IGA for fault tolerance, but we could use it for field personalization of the circuit.
I know what you mean. The thing is that it depends where the IGA bulk is fabricated. If you don't have access to photolithography technique to build the IGA bulk, it means that you are using maybe some digital printing or some analog printing techniques which do not provide you 100% yield. So in that scenario, you need to test the transistors to see if all of them are working or not. But if you're building your IGA bulk in photolithography technology, we can expect to have 100% yield and skipping the fault tolerance step and using digital printing techniques to customize the gate array.
Then, as far as I see, we wouldn't need to work at the transistor level. In fact, I think that the name of your proposal is wrong. Shouldn't it be inkjet configurable transistor array instead of gate array?
Yeah, but I think this is the same concept in the gate array in early 80s. Gate arrays are not built of complex gates, but they are built of transistor arrays, being later on customized for final circuit functionality. So we are taking the same concept from silicon gate array, which is built of transistor arrays, and we are mapping that to organic electronics. But yeah, it could also be named as inkjet configurable transistor array, and when we have cell-based gate array, we call that inkjet configurable gate array.
Okay, another concern for me is eco-friendly. And so I see that one of the justifications of having printed electronics is one of them is that we're using additive technologies instead of subtractive ones. But then most of your work is working with subtractive technologies, and then you just drop the final drops in which you don't waste much. So I see you wasting a lot of material.
Yeah. Well, my answer is if you are going to go for eco-friendly and only additive manufacturing electronics for print electronics, it is still far away for implementation of high-performance circuits. So if you need a high-performance circuit, still the circuit needs to be either by silicon-based materials, or if you are using organic materials, it should be fabricated using clean room processes like photolithography. Because comparing them to the behavior of non-photolithography techniques like inkjet, gravure, or whatever, the yield is low, the density is much lower than photolithography, and the performance of the devices are not even comparable with photolithography devices. So if you are aiming to have some mid-performance, even mid-performance electronic circuits, it is desired to have either inorganic materials or photolithography techniques. But the discussion about being environmental friendly and having more only additive manufacturing comes to the applications where the large area and flexibility are important, like photovoltaics or solar systems.
So would it be possible to remove all the wiring, pre-existing wiring that you do at the clean room facilities? Could you remove it and implement it with only inkjet printing?
Yes, it is possible, but I don't see the reason for that as long as we are having the transistors fabricated in photolithography. So if the transistors are still in photolithography, so the mask is already prepared. So why not we also use the pre-patterned wire cells in photolithography as well, and just for customization we leave the inkjet printing. Because if we want to have both of pre-patterned wire cells and the final customization by inkjet, we will reduce the density dramatically. Comparing to the size of photolithography transistors, the wire cells would be much larger.
I look at, for instance, slide 65, and I see quite a big overhead in area because of the wiring.
Exactly. And those are all being fabricated by inkjet, both the transistor and the wiring. And this is the photo. All the transistors and wire cells are fabricated by inkjet here. And although, well, we cannot see the comparison in size between this one and...
Yeah, well, of course. Right.
And this one, but as you see, the photolithography one is occupying 1.4 centimeter square, and the all inkjet gate array is occupying, you see, 7.9 multiplied by 13 centimeter. So it is, I think it is like 20 times bigger than the other one. So this is the idea of fabricating the transistors and pre-pattern uncommitted wire cells by photolithography, which is high performance and high resolution, and just realizing the final customization in the field by a very simple and low complex inkjet printing.
So I'm so curious about the ratio between drive and load
Yeah.
transistors.
Mhm.
How did you come up to that
Well,
number?
It's a good question, because I designed like starting from 3 to 20 for the ratio and tested all the devices, all the circuits, and 8 for this technology and 7 for the other technology is showing the best results. All of them are presented in chapter 4, but because I have done, during the thesis, I have been involved in several projects, and it has been a lot of work comparing to fitting all of that in 1 hour, I skipped chapter 4. But you see that how we develop this process and the cells in chapter 4.
Okay. Just one mention I
Sure.
remember. When describing CMOS, you said that there was no shortcut between... when you describe in logic,
Yeah.
you talked about CMOS, and you said that there was no shortcut current between VCC and ground.
Yeah.
And actually there is when there is a transition. So it's...
You mean the leakage current?
Not leakage, but when there is a transition between 1 and 0, you have for a period of time a shortcut current.
Yeah.
Just a minute.
Yeah, there is a very short period of time that
Yeah.
this is happening. But when we are having the pure 1 and pure 0, there is no...
I know why you say so, but just a minor question.
Maybe I shouldn't be that 100% saying that, yeah.
Just my final question about the motivation. When you were describing in the initial slides the type of circuits that you could build, you were mentioning RFID.
Yeah.
And then see your foil, which can be customized, but out of this foil, I don't see an RFID tag with that. So my question would be, what could you build with that, which is with the actual foil that is nowadays has some industrial application?
I think I didn't get your question exactly.
So your circuit is a piece of paper or a plastic or substrate with some circuit that you can customize.
Yeah.
Why should I use this technology for an industrial application? What can I build with this that justifies to use this technology?
Okay. Yeah.
Instead of substituting a system implemented with other technologies.
Well, yeah. Okay. I think I got your question, and my answer would be, if you require large area and flexibility, you should go for this technology. But if you're I'm sorry.
So I'm just wanting an example.
Yeah.
For instance, if I require, if you require large area and flexible, put me an example.
Yeah. For example, here, as I said, display driver circuitry. If you can have the controller circuitry, the row selector and column selector of the display being realized in a flexible technology, that would be much better, because you bring the flexibility also to the end point.
Okay.
Yeah, rather than having a silicon chip.
Okay, thank you.
Okay. Thank you very much. So now it's my turn to ask a question. First of all, I want to congratulate you for your very excellent presentation and also high-level thesis dissertation.
Thank you.
I found, well, your text quite clear, and the results were well explained, same as for your talk. But well, I had a few questions. Some of them actually have already been asked by other committee members. But I have one additional questions regarding the fault tolerance technique, because you say that you don't apply it when we use a lithographic process,
Yeah.
but otherwise we have to apply it and we have to test every transistors. Do you think would there be any other alternative technique where it would not be necessary to test all of them, or do you think it's absolutely necessary because the yield is low, is 50%? But do you think there are alternative techniques?
Okay, good and challenging question. Actually, I think it totally depends on the technology. It totally depends on what technology we are fabricating the ego bulk with. If you're talking about 50% yield, I think there is no other way except just testing the transistors, because you cannot trust it. But if there is a technology like providing something like around 80 or 90% yield, like at least expected, one of the solutions that I already mentioned is that we can start metallizing, customizing several number of foils to the same functionality and stop when the first one is working. It means stop when we are using the all working transistors actually by chance on the substrate in order to build that circuit. But I still believe that it is not this efficient way of doing that, because as I said, the yield is with some small tolerance different from foil to foil, but more importantly the failure map is different. So we don't know which of these transistors are working and which of them are not. One way would be to check, to kind of scan the transistors optically to see if we see any short between drain and source, or some kind of optical characterization to see the initial problems, failures that could have happened during the process, and skip those obvious defects and only go for something that is at least not optically observed. But I'm not sure if still we can get the nice results or not. But for further techniques, nothing has happened to my mind yet.
Yeah. So this means that you say we should know first of all which is the typical yield of the technology. So we know that it's 50%. No way. We have to test all. We know that it's higher, but if you say 85, 90%, then there could be maybe alternative techniques, although, well, you are somewhat skeptical. But anyway, do I understand that first of all you need to know the yield for each technology? Is it right?
Exactly.
Typical yield.
Exactly.
Okay.
And this is realized by just testing several number of transistors in different runs. Yeah.
Okay. Another related question is when to test each one of these transistors, which are the characteristics you need to measure? I mean, transfer, output, gate current, or all to test the transistors?
Actually, what we are planning is to see if the transistor is working first of all, which is checking some stresses like the short between drain and source, short between gate and electrodes. The other thing is that if the transistors has enough sufficient performance to be used as the circuit, and usually that is done by testing some eye on over eye off ratio, if it is sufficient enough, and some mobility characterization to see if the mobility is comparable to the other ones, in order to have a kind of uniform circuit where some transistors are not weaker than the other ones.
So you need to do all these tests to each transistor.
Ideally, yes.
Yes. Okay, thank you. Well, I have another question. It's regarding simulation, because for the design, then I understand that you are using a design kit, and well, I imagine you have to perform simulation before doing the fabrication, but how about the models included in this design kit? Are they really specific for TFTs, or just SPICE 1, SPICE 2 for silicon? Because you mentioned about the models that were used by people, but the many kits that was like this, just basic MOSFET model. But in your case, which model did you use for the simulations?
Actually, as I said, we haven't yet modeled the devices. Actually, the modeling has been done, but not till the late stages of the thesis. But if we need to simulate the circuit, I would again go for the fact that it depends what circuit and what implementations are we going to have on top of the IGA. So if it is just being very simple logic circuits like multiplexer, like the encoder, decoders, as I said, for the display driver, so maybe low-level modeling would be enough. But if we want to go for some more analog behavior and more details, behavior and more complex circuits for amplifying and like for other applications, maybe we need higher levels of modeling.
But then you didn't do simulations of the circuits?
No, not yet, no.
Okay,
This
but
is-
you can with the design kit, are there?
Yeah. Yeah.
Okay,
Yeah.
okay, thank you. Okay, and one more general question. Among your results presented in this thesis, which result do you think will be the one will have or has more impact potential?
I think the fact that we can use low resolution digital printing like inkjet, which is the most common and available one, and cheaper comparing to the other fabrication technologies, the fact that we can use that for uncommitted array of high performance transistors using this drop configurable structure just by leaving one drop and having a circuit built at home, not returned to the manufacturer, but at home, would be the main impact of the thesis, which is one of the advantages of IGA, bringing more functionality capabilities to the IGA.
Okay, so thank you very much for your answers. I don't have any more questions. So now the jury will discuss about the thesis. So both the. Do you have a question?
No, maybe.
Oh yes, sorry, I forgot. Does anyone in the public have a question? But the condition is that that person must be PhD. Otherwise, no? No questions? Yeah, oh, okay, there's one. Okay, thank you.
I have a question. It's a very general question.
Sure.
What did you enjoy most about doing your PhD?
That's a good question.
I think this was the first time that I had the chance to deal with some real-world technologies and having the chance to take the advantages of some high performance and complex technologies like at CPI or New Drive, and also the chance that I could use digital printing techniques, different digital printing techniques at CPI, at CNM, at University of California, and bringing all of these chances together and integrate them to one thesis to end up to some results. What was the thing that I actually didn't expect at the beginning, but when it happened, it is the thing that I'm kind of enjoying from that. It is very strong to say I'm proud of, but I'm enjoying from that. Yeah.
Okay. Any more questions? No? Okay, so now finally the jury will privately meet to discuss about the dissertation and agree on the score. So now both the PhD candidate and the public must leave the room, and when we have made a decision, then we will call the candidate. Also, the public will be able to come.